Somewhere in the ocean tonight, a whale has stopped moving. At first, the sea may give almost no sign that anything important has happened. The waves continue to rise and fall. The wind moves across the surface. Light still breaks apart on the water in the same way it did a few minutes earlier. But beneath that ordinary surface, something enormous has changed. A body that once moved through whole oceans is now still. For years, this whale may have crossed thousands of kilometers of open water. It may have dived into cold depths, returned to breathe, followed seasonal food, carried sound through the sea, and moved with the slow confidence of one of the largest animals ever to live on Earth. Now it drifts. For a while, trapped gases may hold the body close to the surface. Currents turn it gently. Waves push against it from different directions. From a distance, it might look almost like a floating island of dark skin and pale scars, still massive, still recognizable, but no longer alive. The first animals may find it before it sinks. A shark moving through the upper ocean can detect the body from far away. Seabirds may circle if the whale remains close enough to the air. Small pieces of tissue can loosen and drift downward before the main body has even begun its descent. The surface feeding can begin under daylight. But the deeper story has not started yet. That story begins when the body finally loses the last of its buoyancy. Gas escapes, water enters. The balance changes quietly. Then the whale slips beneath the waves. The surface closes above it, and the body begins to fall through the ocean. A whale does not sink through empty space. It passes through a living, layered world. At first, the water around it may still be blue. Light from above follows it down for a while, growing weaker with every meter. The shape of the body remains visible, but less clearly now, as if the ocean is slowly taking back its outline. Farther down, color begins to leave. The warmth of the upper ocean fades. The pressure rises. The whale turns slightly as it sinks, pushed by currents that move through the water in slow, invisible sheets. A bubble may escape and rise behind it, going back toward the surface while the body continues downward. At around 200 meters, sunlight has already lost most of its strength. At 500 meters, the ocean is almost completely dark. Below that depth, the whale enters a part of the planet where daylight has no meaning. This darkness is different from night. Night belongs to the world above. Night has air, stars, moonlight, and the promise that morning will return. The deep ocean has a darkness that does not lift. It has covered the seafloor for millions of years. The whale continues through it, falling past animals that live without any memory of the sun. Some carry their own light in their bodies, producing flashes of blue or green that last only a moment before the black water takes them back. Others are nearly transparent, shaped by pressure and scarcity into forms that would seem impossible at the surface. Most of these animals will never touch land. Many will never see daylight. The whale passes through their world as something strange and temporary, a vast shadow moving downward through cold water. For a large whale, the descent may last hours. If the seafloor is especially deep, the body can pass through kilometers of water before it reaches the bottom. During that time, the carcass continues to change. Tissue softens. Fluids leak into the water. Chemical traces spread outward through the darkness. Long before the whale lands, it is already announcing itself. In the deep sea, food is scarce enough that chemical signals matter. A faint trace of organic material can draw the attention of animals adapted to long hunger and slow movement. A dead whale releases something far stronger than a faint trace. It sends oil, blood, tissue, decay, and disturbance into a world where large meals almost never arrive in one piece. Down on the seafloor, the usual food supply is thin. Most life there depends on what falls from the sunlit ocean above. Tiny remains from plankton, waste from animals, broken biological material, and fine organic particles drift downward through the water column. By the time this material reaches the deep bottom, it may have been falling for days or weeks. Scientists call it marine snow. The name sounds soft, but the reality is severe. Marine snow keeps the deep seafloor alive, yet it usually arrives in amounts so small that animals must live carefully. Energy is spread thinly over huge distances. Many creatures move slowly because speed is expensive. Bodies are built around patience because the next meal may not come soon. A whale fall changes that entire pattern. When a whale lands on the seafloor, it brings a concentration of energy that the surrounding area might otherwise receive only after centuries of ordinary drift from above. Tons of flesh, fat, bone, carbon, nitrogen, sulfur, and mineral-rich tissue arrive in one place. For the animals nearby, this is not simply a larger version of normal food. It is a rare event powerful enough to change the chemistry, the population, and even the physical structure of the seafloor around it. Eventually, the whale reaches the bottom. The landing may be soft if the sediment is fine, or heavier if the body strikes harder ground. A pale cloud of mud can rise around it and drift slowly back down. The carcass settles into the seafloor, pressing its weight into a place that may have been nearly flat and quiet for a very long time. For the first time, the whale is no longer part of the open water. It has become part of the bottom. The first major stage begins with animals that can travel to the carcass while the soft tissue is still available. Scientists call this the mobile scavenger stage, but the name makes it sound more orderly than it looks. The scene is slow compared with a feeding frenzy at the surface, yet for the deep ocean, it is intense. A place that may have seen little movement now becomes a center of activity. Sleeper sharks are among the most striking visitors. These sharks belong to cold, dark environments where life runs on a slower clock. Their metabolism is adapted to long periods without food, and their movements are usually economical. A whale fall gives them access to a meal so large that it can justify travel, competition, and repeated feeding. A sleeper shark may approach from the darkness, take hold of the soft tissue, and pull away pieces with a force that seems almost out of place in such a quiet world. Hagfish often arrive too. They are ancient, eel-like scavengers with soft bodies and a feeding style that feels almost unreal. A hagfish can push into dead tissue and work from inside the carcass, reaching flesh that larger animals may not remove cleanly. When threatened, it can release thick slime into the water, an adaptation so effective that many predators avoid dealing with it. Crabs, amphipods, and other scavengers gather around the body as the signal spreads. Each animal uses the carcass differently because each body is built differently. A shark can tear away large sections. A hagfish can enter the soft interior. Smaller scavengers clean edges, wounds, openings, and scraps left behind by larger mouths. The whale changes shape under all of this attention. The soft organs are consumed early. Muscle begins to disappear. The thick blubber layer, which once helped the whale store energy and survive in cold water, becomes one of the richest parts of the feast. The body collapses in places as internal support is removed. Skin loosens. Exposed bone appears through torn tissue. The seafloor around the carcass becomes marked by fragments, fluids, and disturbed sediment. In some observed whale falls, large carcasses have been reduced to skeletons within months. Where scavengers are especially abundant, parts of the process can move even faster. But decomposition in the deep sea should not be imagined as simple erasure. The whale is being transferred. Material that once belonged to one living animal begins moving through many lives. A piece of muscle becomes energy for a shark. Soft tissue that falls into the mud feeds microbes and tiny invertebrates. Waste from scavengers enriches the sediment around the body. Animals that feed well may grow, move farther, or reproduce. The whale's form is breaking apart, but its biological material is spreading through the deep sea. That is the first transformation. A whale that once gathered energy in the surface ocean is now releasing it into a world without sunlight. For years, the animal lived by breathing air and feeding in water connected to the sunlit layers above. After death, its body carries that surface energy downward, delivering it to organisms that could never have reached it otherwise. This is why whale falls feel so strange. They connect two worlds that seem separate. The bright ocean above builds the whale. The dark ocean below receives it. After the first scavengers have done their work, the body no longer looks like the animal that once moved through the sea. The outline is broken. The soft tissue is mostly gone. What remains is a skeleton surrounded by altered sediment. At first glance, bones might seem like the end of the feast. In a whale fall, they are closer to the beginning of a slower and stranger phase. Whale bones are rich in oily material. Inside the dense structure of the skeleton, lipids remain protected after the flesh has been removed. Scavengers can strip the outside, but much of the energy inside the bone is locked away, from teeth, claws, and scraping mouthparts. That hidden energy is one reason a whale fall can last so long. The skeleton of a large whale can contain thousands of kilograms of lipid-rich material. It will not be released quickly. Instead, it becomes available slowly, through microbial action and chemical change, across years and sometimes decades. While that long process is beginning inside the bones, the area around the skeleton is already changing. During the first stage, scraps of tissue have fallen into the sediment. Fluids from the body have seeped downward. Waste from feeding animals has accumulated. Microbes have begun breaking down organic material in the mud. The seafloor near the whale becomes richer than the surrounding abyssal plain. To a human eye, the difference might look small. There is mud, bone, darkness, and a few animals moving slowly through the lights of a submersible. Chemically, though, the place has been transformed. The sediment now holds more organic matter. Microbial activity increases. Small animals that normally survive in low numbers can find more food in the mud around the skeleton. Worms move through the enriched sediment. Tiny crustaceans feed in the altered patch around the bones. Microbial films begin to spread across surfaces that were once clean or bare. The change does not stop at the exact outline of the whale. It expands into the surrounding seafloor, creating a zone of enrichment that may extend several meters from the carcass. On land, a few meters may sound insignificant. In the deep sea, where food is scattered thinly across vast distances, a few enriched meters can matter enormously. The skeleton also changes the physical environment. Much of the deep seafloor is soft sediment, wide and nearly flat. Hard surfaces are rare. When a whale skeleton arrives, it adds shape to a place that had little structure before. Ribs rise from the mud. Vertebrae create edges and hollows. The skull can become a large, irregular shelter. Currents move differently around the bones than they did across the flat sediment. Particles collect in new places. Small animals find surfaces where they can attach, feed, hide, or move through. The whale is no longer only food. It has become architecture. This middle stage is easy to overlook because it is not as dramatic as sharks feeding on soft tissue, and it does not yet have the strange chemical intensity of the later bone stage. But it is where the carcass begins to become a place. The deep-sea city is not built all at once. It grows from changes in food, structure, sediment, and chemistry. A body becomes a landscape because the seafloor around it now offers things that were not there before. More energy, more shelter, more surfaces, more microbial growth, more reasons for animals to remain. As months pass, the whale fall becomes less recognizable as a corpse and more recognizable as a small ecosystem. The next stage begins in a hidden way, inside the bones themselves. As bacteria colonize the skeleton and the oxygen inside parts of the bone and sediment becomes limited, anaerobic microbes begin breaking down the lipids. These microbes can live where oxygen is absent or scarce. Their work produces hydrogen sulfide. Near the surface, hydrogen sulfide is mostly known as dangerous. It is toxic to many organisms and carries the smell associated with rotten eggs. In the deep ocean, under the right conditions, that same compound can become the basis of life. Hydrogen sulfide seeps from the bones and the surrounding sediment. As it spreads, it creates a chemical gradient around the skeleton. Chemosynthetic bacteria use that chemical energy to build organic matter in darkness. This is one of the most important ideas in deep-sea biology. For a long time, scientists understood ecosystems through sunlight. Plants on land and phytoplankton in the ocean captured solar energy, and animals received that energy by feeding directly or indirectly on them. The sun seemed to sit at the base of everything. Then researchers discovered hydrothermal vents in the deep ocean and found entire communities thriving without sunlight. Those vent ecosystems were powered by chemistry rising from the seafloor, not by photosynthesis. Whale falls revealed another path to a similar kind of life. A dead whale could create a chemical ecosystem without volcanic heat. The energy came from the body, more precisely from bone, fat, bacteria, and time. As chemosynthetic bacteria grow, they can form visible mats across the whale bones. Under the lights of a remotely operated vehicle, these mats may look pale, yellowish, or orange. They coat surfaces that once belonged to a living skeleton and turn them into feeding grounds. Small animals gather around these bacterial communities. Worms move across the bones. Snails and limpets can feed from the microbial growth. Crustaceans explore the sediment and hard surfaces around the skeleton. By this stage, the whale fall has become something far more complex than a carcass being eaten. It is a chemical habitat, a structured community, and a rare patch of abundance in a dark environment where energy usually arrives slowly and in tiny amounts. The city metaphor begins to make sense here. There are no streets, walls, or buildings, but there is organization. Different parts of the whale fall offer different resources. The sediment carries one kind of opportunity. The bone surface offers another. Deep inside the skeleton, microbes are working on energy that larger animals cannot reach. Around the bones, chemical gradients shape where certain organisms can survive. Nothing here was planned. No creature is building the whole system intentionally. The city forms because life responds to energy wherever it appears. One of the most remarkable animals associated with whale falls is Osedax. Its name means bone devourer. When researchers first described Osedax in the early 2000s, the visible part looked delicate, almost like a small red plume rising from the bone. In the current, it could move gently, giving the strange impression that something flower-like was growing from a skeleton in total darkness. The rest of the animal was hidden inside the bone. Osedax has no ordinary mouth. It does not chew in the way most animals do. It has no normal stomach for digesting pieces of food. Instead, it sends root-like tissue into the whalebone. Inside those tissues live bacteria that help process compounds from the skeleton. The worm depends on that partnership to draw nutrition from a source most animals could never use. That makes Osedax one of the clearest examples of how specialized whale fall life can become. This animal is not simply visiting a dead whale. Its body is shaped around the existence of dead whale bones. Its life makes sense because, for millions of years, large marine animals have died, sunk, and left skeletons on the seafloor. The reproductive biology of Osedax is even stranger. The visible worms are female. The males are microscopic and live inside them, reduced to tiny bodies focused almost entirely on reproduction. From a human point of view, this seems extreme, but the deep sea is not shaped around human expectations. Evolution keeps whatever works. At the bottom of the ocean, on a temporary island of bone and chemistry, this arrangement works. Osidax is not the only specialized organism in this world, but it captures the larger truth of whale falls better than almost anything else. A whale fall is not a pile of remains. It is a habitat that has existed often enough, for long enough, that evolution has built bodies specifically for it. As years pass, the whale fall continues to shift. The first scavengers may be gone. The soft tissue may have vanished. The sediment remains changed, but the early pulse of loose organic material becomes weaker over time. Inside the bones, the slower chemistry continues. Different parts of the skeleton release energy at different rates. A rib may support thick microbial growth, while another bone is already declining. The skull, vertebrae, and larger bones can each become small zones within the larger system, with their own surface growth, microbial activity, and animal communities. The whale fall is never frozen in one stage. It is a slow, ecological sequence. On land, people often understand succession through forests returning after fire, or abandoned fields slowly becoming woodland. At a whale fall, succession happens through decomposition, enrichment, microbial chemistry, and the gradual exhaustion of bone. The body arrives. Scavengers open it. The sediment changes. Bones begin releasing chemical energy. Bacteria build a new foundation. Animals adapted to that foundation gather. Eventually, even the bones begin to run out. The full process can last far longer than the first feeding event suggests. A large whale skeleton may sustain sulfide-based communities for decades. In some estimates, the bones of the largest whales can support life for 50 to 100 years, possibly longer under certain conditions. That means a whale dying tonight could still be shaping one patch of seafloor when a child born this year has grown old. One breath stops near the surface. A hidden ecosystem begins below. The scale is difficult to fully absorb. A whale spends its life in motion, crossing ocean basins, breathing air, diving through water, feeding in the upper ocean, and carrying the energy of the surface world in its body. After death, that same body reaches a place where sunlight never arrives. There, it begins to support animals, microbes, and chemical processes that belong completely to the deep. The whale does not remain recognizable forever. Its shape disappears. Its tissue is consumed. Its bones are colonized and slowly broken down. But the material continues moving. It becomes part of sediment chemistry, microbial growth, animal bodies, and the long biological rhythm of the seafloor. In the deep ocean, death is not simply the end of a body. It can also be one of the ways energy arrives. That is why whale falls matter. They reveal what the deep sea can do when a rare concentration of food and structure appears in the dark. The surrounding world may look empty to us, but it is not empty. It is slow, scattered, and difficult to observe. When a whale lands, that hidden life becomes visible because the energy finally has a center. Animals arrive from the darkness. Microbes spread through bone and mud. The sediment changes. The skeleton becomes a surface, a shelter, and eventually a chemical engine. A dead whale reveals the deep sea's capacity to organize around opportunity. Scientists are still learning how complex these systems are. Every whale fall is different. Depth, temperature, whale size, sediment type, local scavengers, and ocean currents all shape what happens next. A small whale will not create the same long-lasting habitat as a giant blue whale. A carcass in one ocean basin may attract a different community from one in another. Even the speed of the first feeding stage can change the stages that follow. The deep sea is hard to observe, which means much of this process still happens beyond human sight. Researchers have discovered natural whale falls by chance, and have also placed carcasses on the seafloor to study how communities develop. Each observation adds a little more detail, but the ocean is vast, and most whale falls will never be seen by scientists. That may be part of what makes the subject feel so powerful. Right now, somewhere on the planet, one whale may be floating at the surface. Another may be sinking through black water. A third may already be on the seafloor with scavengers feeding around it. Far away, an older skeleton may be covered in bacterial mats and bone-eating worms. Somewhere else, the last chemical traces of a whale that died decades ago may be fading into the sediment. These events do not wait for us. They are part of the ocean's long routine. A whale dies, the body falls, the seafloor changes. Life gathers, feeds, grows, reproduces, and slowly moves on. What remains is not a clean ending. It is a footprint in the deep, a changed patch of sediment, a chemical memory, a place where one animal continued shaping life long after its own life had ended. For now, stay with the beginning. The whale has reached the bottom. The first scavengers have found it. The soft body is being opened. The sediment around it is already becoming richer. Microbes are starting work that will continue long after the large animals leave. Inside the bones, hidden energy waits. The city is not fully formed yet, but the foundation is already there. A body on the seafloor, a rare concentration of energy, a skeleton that will become structure, a chemical future sealed inside bone. Around it, the deep ocean begins to organize with a patience that belongs to darkness, cold, and pressure. In part 2, we will move deeper into that hidden city. We will look more closely at the animals that depend on whale falls, the strange biology of bone-eating worms, the connection between whale skeletons and hydrothermal vents, and the possibility that dead whales helped deep-sea life move across the ocean floor for millions of years. But for now, imagine the scene far below the surface. The water is near freezing. The pressure is immense. No daylight reaches the sediment. The whale rests in the dark, no longer alive, but no longer simply still. The body has begun to open. The bones are waiting beneath the remaining tissue. Bacteria are already spreading into places no larger animal can reach. The darkness around the whale has changed. Something has started there, quietly, slowly, almost invisibly. A dead whale has reached the bottom of the sea, and in the place where it falls, life begins building a city. Years after the whale first reached the bottom, the scene would no longer look like a carcass in the ordinary sense. If a remotely operated vehicle came across it in the dark, its lights would reveal something stranger than a skeleton. The bones would be partly buried in sediment, partly exposed to the cold water, and covered with the slow evidence of life. The soft tissue that once attracted sharks and hagfish is gone. The large scavengers have moved away. What remains is not clean, or empty, or finished. It is a place that has been changed. A rib may carry a pale layer of bacterial growth. The skull may have settled into the mud at an angle, with small animals using its hollows as shelter. A vertebra that once helped support one of the largest bodies on Earth may now look almost like part of the seafloor itself, softened by time, and altered by organisms that have been working through it for years. From a distance, the sight might seem quiet. That is one of the misleading things about the deep ocean. So much of its life happens slowly, and because it does not move at a human pace, we can mistake it for stillness. But an old whale fall is not inactive. It has simply entered a slower, more chemical part of its life. The first stage was easier to understand. A body arrived, and scavengers fed from it. That kind of scene makes sense to us, because it resembles feeding events we recognize from the surface world. The later stages are stranger, because the whale is no longer giving itself away as flesh. The remaining energy is hidden inside bone, inside altered sediment, inside bacterial communities, and inside reactions too small to see directly. This is where the deep sea becomes difficult and fascinating at the same time. A whale fall does not become less important when the obvious feeding ends. In many ways, it becomes more unusual. The site shifts from a meal into a habitat, and then into something closer to a chemical system, built around the remains of one animal. Researchers have now observed enough whale falls to know that they tend to follow a broad sequence, even though each one develops in its own way. A carcass in cold, deep water will not change at the same speed as one in shallower conditions. A giant whale leaves behind a much longer-lasting resource than a smaller animal. Soft sediment absorbs fluids and organic material differently from firmer ground. Currents can carry chemical signals away from the skeleton, and they can also bring larvae from distant habitats. Even the whale's condition before death can influence what happens next, because the body carries the biological history of its final months. So every whale fall has its own character. One site may be stripped quickly by scavengers, while another develops a dense bacterial community around the bones. In a place where specialist animals are rare, the later stages may unfold in a completely different way. The important point is that the carcass keeps changing the environment, long after the body stops looking like a whale. The older skeleton is temporary, but temporary does not mean brief. In the deep ocean, a large whale fall can remain important for decades. The bones release energy slowly because much of the fat inside them is locked in dense tissue. Bacteria and specialized animals need time to reach that material, break it down, and turn it into something the surrounding community can use. That slow release is what allows a whale fall to support life, long after the first scavengers have disappeared into the dark. This slow timeline connects whale falls to one of the most important discoveries in deep-sea science. In the late 1970s, scientists found hydrothermal vents near the Galapagos Islands. Before that discovery, many researchers expected the deep seafloor to be extremely poor in life, because sunlight could not reach it. Then cameras descended into the dark and found communities living around cracks in the seabed, where hot, mineral-rich water was rising from Earth's interior. The animals there were astonishing. Huge tube worms stood in the darkness. Clams and mussels gathered around the vent fields. Shrimp and crabs lived in water shaped by chemistry rather than sunlight. The foundation of that ecosystem was bacterial. Those bacteria were using chemical energy from the vent fluids to build organic matter. Larger animals lived from that production, either by feeding on the bacteria or by carrying bacterial partners inside their bodies. This process is called chemosynthesis, and it changed the way scientists thought about life on Earth. It showed that sunlight was not always required at the base of a food web. What life needed was usable energy. In the right environment, that energy could come from chemical reactions. Whale falls create a quieter version of that idea. A dead whale does not bring volcanic heat to the seafloor. It does not open a crack in Earth's crust. The chemistry comes from the body itself. As bacteria break down fats inside the bones, hydrogen sulfide can seep into the surrounding sediment and water. Near the surface, hydrogen sulfide is usually understood as dangerous. In the deep sea, under the right conditions, it can become fuel for bacterial life. This is why the later stages of a whale fall matter so much. The skeleton becomes a sulfide-rich habitat, and in a biological sense, that makes it resemble other chemical environments, including hydrothermal vents and cold seeps. These places are not identical. A vent is powered by geology. A cold seep is shaped by compounds rising from the seabed. A whale fall begins with the death of an animal, but all of them can create conditions where bacteria use chemistry as an energy source. That connection raised a major question for scientists. Hydrothermal vents are scattered across the ocean floor. They form only where geology allows them to form, often along spreading centers, volcanic regions, or places where hot fluids can move through the crust. Between one vent field and another, there may be hundreds or even thousands of kilometers of deep seafloor. For many adult vent animals, that distance is impossible. They cannot simply travel across the abyss until they find another vent. Their larvae, however, can drift in currents. These tiny young stages may move far from the place where they were born, but they still have limits. They need to find a suitable habitat before their energy runs out. This is where whale falls may become important. A whale skeleton lying between distant chemical habitats can act like a temporary stopover. A larva drifting through the deep ocean may not find a vent immediately, but if it reaches a whale fall with the right chemistry, it may be able to settle there, grow, reproduce, and send another generation outward. Over very long periods, that kind of pattern could help organisms move through the deep sea in stages. This does not mean every whale fall becomes a bridge between hydrothermal vents. The deep ocean is far too complex for that. Many larvae never find the right place. Many carcasses land where the needed species are absent. Some skeletons are too small or too short-lived to support the right chemical conditions for long. But across millions of years, with whales dying and sinking throughout the world's oceans, these temporary habitats may have been common enough to influence how deep-sea life spread. That idea makes the whale larger than its body. While alive, a whale moves nutrients through the upper ocean. It feeds, migrates, dives, breathes, releases waste, and helps circulate material through marine ecosystems. After death, the same animal can carry surface energy into the abyss, where it may support organisms that live in complete darkness, and perhaps help connect habitats that are otherwise isolated. This also makes the history of whaling more disturbing than it first appears. Commercial whaling removed millions of large whales from the ocean. At the surface, the damage was visible. Whales disappeared from feeding grounds. Migration routes became quieter. Breeding populations collapsed. Blue whales, sperm whales, fin whales, humpbacks, and other large species were reduced dramatically. The ocean itself became quieter in places where whale songs had once traveled through the water. But every whale removed from the sea was also a body that would not complete the natural cycle of dying, sinking, and feeding the deep ocean. That does not mean every hunted whale would have become a large whale fall. Nature is more complicated than that. Some bodies would have floated longer. Others would have been consumed near the surface or broken apart before reaching the abyss. Still, when millions of large whales disappear from the ocean, the number of bodies reaching the deep seafloor must change as well. The difficult part is that this loss leaves almost no obvious mark for us to see. A forest cut down leaves a visible gap. A destroyed reef can be photographed. A missing whale fall is different. It is an event that never happened, in a place humans rarely observe. No one sees the empty patch of seafloor and recognizes what should have arrived there. The sediment simply remains poor. The bones never bring their chemistry. The animals that might have used that habitat never gather, because the habitat never has the chance to form. This is not easy to measure, but the possibility is powerful. Human activity at the surface may have changed the deep ocean in ways that scientists are only beginning to understand. A whale taken for oil and meat was not only removed from the living ocean, it was also removed from the future ocean floor. That changes the meaning of whale conservation. When whale populations recover, we usually think first about the living animals. We think about their songs, their migrations, their calves, their role in surface ecosystems, and the awe of seeing them alive. All of that matters. But recovery also means that more whales may eventually complete the full ecological cycle. A whale that lives, dies naturally at sea, and sinks, can still become part of the deep ocean's long system of renewal. Protecting whales in that sense is not only about preserving life while it is visible to us, it is also about allowing the ocean to keep receiving what whales give after death. Now return to the old skeleton on the seafloor. Decades may have passed since the whale first landed. The bones are weaker now. Ocedax worms may have spent years tunneling into them. Bacteria have been processing the fats sealed inside the bone matrix. A rib that once helped support an enormous living body may now be porous and fragile. A vertebra that once seemed solid can become filled with tiny channels. Parts of the skull may be buried in mud, while other surfaces remain exposed to slow currents. At this age, the whale fall has a different feeling. The dramatic feeding stage is long over, and the later chemical stage may be uneven. One part of the skeleton may still support bacterial growth, while another part has already lost most of its remaining energy. The site does not fade all at once. It weakens in patches. The sediment close to the bones may still carry the history of the whale. For a long time, it can remain richer than the surrounding mud. Microbial communities may be different there, and chemical traces can persist after the thickest bacterial mats are gone. A few meters away, the deep sea floor may look sparse again. Near the remains, the whale's influence can continue. Even when the strongest chemistry fades, the bones can still matter as physical structure. In many parts of the deep sea, hard surfaces are rare. A remaining bone can give small animals something to attach to. A hollow can collect particles drifting through the water. A broken edge can create shelter from weak currents. The skeleton keeps shaping the small movements of life around it, even as the original energy runs down. There is no exact day when a whale fall ends. Hydrogen sulfide production slows gradually. The bacterial mats become thinner as the bones release less fuel. Animals that depend on the strongest chemical conditions decline, because the place no longer supports them in the same way. Osedax populations fall when the lipids inside the bone become harder to access. The sediment remains altered for a while, but over time, its chemistry begins to resemble the wider seafloor again. The whale does not disappear in a clean moment. It fades into the environment. Its material has already moved through animal bodies, bacterial growth, buried carbon, minerals, and the changed sediment around the skeleton. The place where the carcass rested may hold chemical traces, long after the last obvious shape is gone. That is one reason whale falls change the way we think about death in the ocean. At the surface, death can look like an ending, because we focus on the body as a single form. In the deep sea, the body becomes harder to separate from the processes it starts. The whale stops breathing near the surface, but the consequences of its life continue below. For decades, one animal can influence which organisms live in a patch of darkness, how bacteria grow there, what chemistry becomes available, and how energy moves through the sediment. A single death becomes a long ecological event. This scale is difficult to absorb because most of it happens beyond human attention. A whale may live for many decades. After death, its body may continue supporting life for many more. Its influence can last beyond movement, beyond song, beyond migration, and beyond anything we would normally recognize as the animal's life. Researchers who watch footage of whale falls often describe a quiet sense of awe. A vehicle descends through black water, and for a long time, there may be nothing in the lights but sediment. Then the bones appear. At first, they look like remains, but as the camera moves closer, the surface becomes crowded with detail. Worms move in the current. Crabs cross pale bacterial mats. Tiny shells cling to the skeleton. Beyond the camera lights, the water remains completely black. The scene feels alien, but not empty. Its abundance is slower than the abundance of a reef. It does not explode with color or motion. It builds through bacteria, sediment, chemistry, and patient animals using energy that took years to gather inside a living whale, and decades to release after death. This is why the deep ocean is so easy to underestimate. Humans are brief visitors there. We arrive with machines. We see only what our lights reveal. We stay for a short time, and then return to the surface. The animals below live at a pace that does not match ours. A crab crossing a whalebone is not hurrying for the camera. A bacterial mat is not blooming for our attention. A bone-eating worm is not strange to itself. The deep sea is alive in ways that are easy for us to miss. A whale fall makes that hidden life easier to see, because it gives the darkness a center. For a while, energy gathers in one place. Chemistry intensifies around the bones. Organisms that are usually scattered across the seafloor come together around one source. The process does not happen because it is symbolic. It happens because bodies contain energy, because bacteria can transform chemistry, and because evolution has had millions of years to shape organisms around rare opportunities. Still, from a human point of view, it is hard not to feel the meaning of it. A whale that once rose to breathe in daylight can end up feeding animals that will never know daylight. A body built in the upper ocean becomes the foundation for a hidden world below. An animal that crossed entire basins while alive may, after death, help connect isolated habitats on the ocean floor. That story becomes larger when we remember how long whales have been doing this. Long before human ships crossed oceans, whale bodies were already falling through them. Deep-sea organisms were using whale bones, long before science had a name for whale falls. These hidden habitats appeared and faded countless times before any camera descended into the dark and showed us bones covered in life. We arrived late to this story. The deep sea already had its own systems, its own connections, and its own relationship between death and survival. Whale falls remind us that the ocean is not waiting for human discovery in order to matter. It is an old world, and most of it continues without us. Somewhere tonight, a whale may be sinking through water no person will ever visit. Its body may reach a part of the seafloor that has never been filmed. Scavengers may find it before any scientist knows it exists. Bacteria may begin working inside the bones, and years later, worms may enter the skeleton. The whole process could continue for a century without being seen. That does not make it less real. Many of the most important events in the deep ocean happen beyond human attention. A whale fall is one of them. As an old skeleton weakens, the habitat enters a long decline. The chemical signal becomes faint. Bacterial mats thin as the bones release less energy. Animals that depended on strong sulfide conditions become less common. Sediment can shift over part of the skeleton, and weakened bones may collapse into fragments. Small animals may still use what remains, but the unusual abundance slowly fades. Eventually, the seafloor begins to look more like the area around it. It will not be exactly the same as before, because the whale has changed it, but the difference becomes harder to see. One day, a camera passing overhead might not recognize the place as the site where a giant animal became an ecosystem. That final fading is not a failure. It is the natural completion of the process. The whale has given what its body could give. The soft tissue supported the first scavengers. The enriched sediment fed smaller life. The bones sustained bacteria and the animals connected to them, and the structure created shelter until it began to break down. After that, the deep ocean carries on. Somewhere far away, another whale may begin the same journey. No individual whale fall lasts forever, but the relationship between whales and the deep seafloor is ancient. Each fall is temporary, while the cycle itself has been unfolding for millions of years. Near the end, the site may no longer look dramatic. The bones may be scattered, and the richest bacterial growth may already be gone. The sediment may soften around what remains, but the body has already changed the place. Energy has moved through it. A habitat existed there. Larvae may have drifted outward from it. The deep sea has taken one more large death and folded it into its slow continuity. At the surface, people remember whales through movement and sound. We think of their songs, their migrations, their size, and the moment when one rises beside a boat and breathes. The deep sea knows whales in another way. It receives their weight, their carbon, their bone oil, and the chemistry that appears slowly as the body breaks down. These are not separate stories. They are two parts of the same animal's existence in the ocean. While alive, the whale is a moving presence in the water. After death, the same body becomes part of a slower process on the seafloor. Between those two states is the fall itself, the long descent from breath to sediment. Hold that image for a moment. A great body moves downward through black water. Above it, the surface continues under wind and sky. Below it, the seafloor waits in darkness. The whale does not know what it will become, and the animals below do not understand what is coming in any human sense. But the system is ready, because events like this have shaped the deep ocean for millions of years. When the body reaches the bottom, the first changes begin. Years later, the bones become a source of chemistry. Decades after that, the habitat weakens and starts blending back into the seafloor. The story does not close neatly, because the ocean rarely works in neat endings. Material moves forward in forms too small, too slow, or too scattered for us to follow. A whale fall teaches that death in the deep sea can become transfer. Energy gathered in the surface ocean moves downward and enters the dark. A body that once breathed air becomes food, shelter, chemistry, and a long memory in the sediment. Tonight, somewhere beyond the reach of human light, that transfer may already be happening. One whale may be resting on the bottom with scavengers around it. Another skeleton may be deep in its chemical years. An older fall may be almost gone, visible only through altered sediment and the lives it once supported. Near the surface, another whale may still be moving through the water, unaware that one day its body may become part of the deep ocean's hidden architecture. Most of the ocean is darkness. Most of its stories do not rise toward us. They unfold under pressure, in cold water, at a pace that makes human attention feel brief. Whether we see them or not, they continue. A whale reaches the seafloor and changes the place around it. For a while, a hidden community gathers there. Over time, the bones lose their remaining energy, the chemistry fades, and the sight slowly returns toward the wider seafloor. That is the rhythm of a whale fall. So let the final image become quiet. Far below the surface, old bones rest in black water. The cold slows almost everything. The pressure is immense. Around the skeleton, small animals move across surfaces that once held a giant body together. Inside the last fragments of bone, bacteria may still be turning what remains into usable energy for a world without sun. When the final traces are gone, the whale will not be simply erased. It will have become part of the mud, part of the chemistry, part of the animals that fed there, and part of a hidden network across the ocean floor that we are only beginning to understand. Somewhere else, the next fall may already be beginning. A great body drifts at the surface until the sea finally takes it down. When it reaches the bottom, the darkness around it changes, and patiently, life begins again.